radiation in an enclosure. Now, when we started our analysis of radiation, we knew at that point of time that it's the enclosure with which we are mostly interested in. It could be a furnace or any heating arrangement where you keep a surface which is hot and another surface which is relatively cold, and something, suppose you want to dry something, so you keep it on the cooler surface and you have a surface which is very hot. So, most of the heat transfer from the hot to the cold surface is going to take place by radiation. Now, radiation is complicated by the fact in an enclosure is that there can be multiple reflections. So, you have the hot surface, the energy coming from the hot surface is going to get reflected from the cooler surface, part of it is going to get absorbed as well. So, these kind of multiple reflections between the hot and the cold, as well as the other surfaces, other walls which form the enclosure, they complicate the calculation of radiation. So, one way of taking into account these multiple reflections is not to work with the the black body radiation potential of a surface, rather to work with the potential which an observer is going to experience if he or she is standing just outside the surface, which is known as the radiosity. So, radiosity takes into account not just the inherent emission coming from an object at a specific temperature, but at the same time it also accounts for any reflection which the surface is going to contribute to the total amount of radiation. So, the J radiosity which we have introduced in the last class, there we have seen that there are situations in which J can be greater or less than the radiation potential of a surface. If it is a perfectly black body, then the potential of the object itself and the radiosity of the object, these two are going to be equal, because black body does not reflect anything. So, what we are going to do today is utilize those concepts to see how we can form a network for radiation exchange between an enclosure or between the surfaces forming an enclosure. Before doing that, we would like to assume something. Now, some of these assumptions are going to be valid. I mean, there won't be any questions about it, which would be valid for most of the engineering surfaces. Some of these assumptions are basically for simplification. So, some of the simplifications that we will assume, they are not going to be 100% correct. So, we should understand that which of the assumptions in network method can be questioned, I mean which are not going to be 100% valid. So, I will read the first the assumptions and then we will discuss about each of them. The first assumption in network method is, these are there in textbook, so you do not have to write anything. Radiative properties are uniform and they are independent of direction and frequency. Okay. So, all the radiative properties, what you can think of, for example, reflectivity, transmittivity, emissivity, etc., they are independent of direction, independent of frequency, and all these surfaces are going to be treated as diffuse emitters and diffuse reflectors. So, for all practical purposes, what you are saying is that alpha would be equal to epsilon all the time. That is an assumption which we are going to make, and which is more or less valid for many of the engineering surfaces that we would like to use in our enclosure calculations. The third assumption is that the radiation flux leaving a surface is uniform everywhere. So, if you have a surface which is radiating at all points, you are going to get the same amount of radiation. The third one is the irradiation, that means the radiation falling on a surface is also uniform. So, if you have a 1 square meter surface, all points on that surface is going to receive the same amount of irradiation. So, the last two assumptions which I have said, that the radiation coming from an object is uniform, it is independent of where it is coming from on the surface, and the irradiation on the surface is also uniform. These two may not be met in real practices. So, these two assumptions of network method for radiation exchange can be in error, but still we use it since these two assumptions simplify our calculations to a great extent. So, these are the two which are going to be the main culprits for any errors that might creep in due to our assumptions. And the second one is
So the last assumption that so uniform irradiation.
irradiation.
So that will not hold for different solid angles if you change the solid angle.
True. I mean, if you have one source, if it's a point source and if it is situated far from the surface, then for all practical purposes, we can assume that the irradiation is uniform. But if you have two solid walls in contact making an angle with each other or making a 90-degree angle with each other, which could be true for two walls of an enclosure, then obviously the near the zone where the two walls meet, you are going to have a different irradiation compared to the point where the two are separated from each other. So this is an assumption which is definitely going to be in error. Another condition which we are going to put is that the surfaces are opaque, which is a valid as approximation, because you do not want, you haven't probably seen any radiative furnace with a transparent wall. So radiation, I mean the enclosures are generally made by bricks, fire bricks or so, and those are opaque in nature. So this is also acceptable. Another condition that we are going to put for our calculation procedure, and which is more or less valid, that you either want a uniform temperature or a uniform heat flux. Suppose you would like to dry a material and that material has to be dried, or its temperature should not go beyond certain threshold value. Okay? You are drying a protein, you are drying some other chemicals. Okay? Each one has a temperature above which it starts to degenerate. So you can specify that this is the maximum temperature that my surface can have. So whatever radiative properties or whatever radiation exchange equipment that I am going to design, it should not result in a temperature on the surface which is more than some pre-specified temperature. So a temperature on the surface can be pre-specified. Apart from that, you can also specify heat flux. Suppose you are using as radiative heat source some heater, electrical heater. So you can say that I am going to put only Q watts of energy, maximum Q watts of energy to the heaters. So you can either specify the heat flux or you can specify the temperature. One of these two will be known to you. And the last assumption, which is that the enclosure is filled with non-participating medium. Generally what we have air inside the enclosure, or if you would like to do it in, let's say, carbon dioxide atmosphere or inert atmosphere, for example nitrogen, all these gases are assumed to be non-participating. That means they do not participate in the radiation exchange process in any way. This is also not truly valid, because as we know that there would be some dispersion when radiation moves through a medium, and the gases can also take part into radiation. In the last part of the course, we will see that how the interaction of radiation with the medium, especially with gases present in it, can be taken into account. And you can see that if you have vapors present, water vapors present, more the amount of water vapor present in the medium, then it's going to absorb more amount of energy. It's going to disperse more amount of energy. So the amount of energy that will reach surface 2 from surface 1 will vary depending on what you have in between them. But for the network calculation purpose, we are going to assume that these gases are non-participating. The gases should be non-participating if they are apolar in nature, if there's no polarity. So for air, we can treat them like that's only very small amount of carbon dioxide present, mostly it's nitrogen and oxygen. So you would assume that, well, fine, this air is not participating in radiation in any way. But if you have ammonia present, okay, if you have carbon dioxide present to a great extent, water vapor, then those polar molecules can disperse energy, radiative energy, to a larger extent. So we will assume that it's non-participating medium. Now the next thing that we are going to introduce is the concept of surface resistance to radiation. Now we know that each object is going to emit some amount of energy. Okay, that's going to depend only on the temperature as well as on the emissivity of the surface. So it's simply going to be epsilon times sigma T of the surface to the power 4. It's also going to get some amount of irradiation from other objects, from other walls of the enclosure, and part of it is going to get reflected. The sum total of these two is the radiosity of the surface. So if you think of if you think of the surface with its inherent emissive capability and the radiosity which you are going to experience while standing just outside the surface, these two are not going to be equal except for a black body. So, if these two potentials are not equal, then there has to be a flow of energy from or to the surface. That means, in order to maintain the temperature of the object at a constant value, you either have to supply energy or you have to extract energy. That is in order to maintain thermodynamic equilibrium. So, the amount of energy that you are supplying to the surface to maintain its temperature at, let us say, 500 degrees centigrade is going to depend on what's the EBI. That means the black body, if you have a black body at 500 degrees centigrade, and Ji, which is the radiosity of the real object. Since these two are not equal, the amount of energy that you supply or extract from the surface should also flow in between EB and J. Is this clear? Maybe I'll repeat it again. You have a surface, you have some energy which is coming out of it into the enclosure due to its temperature. You also have a Ji. This EBI and Ji are not equal, since you are also going to have some amount of irradiation on the surface, and part of it is reflected. So, the potential difference between the two must cause a flow of heat. The emissive potential and the radiosity, which is also a potential, these difference in potential will cause some amount of energy to leave the surface or to come to the surface. The net amount of energy you have to supply or take out from outside to the surface. Now, when we are thinking about the heater, okay, the heater, you are supplying some amount of energy to make its temperature at 2000 degrees centigrade. So, it is going to emit some energy, and it is also going to get some energy from other surfaces by radiation, by deflection. Now, the difference between these two is the amount of energy that you are supplying from outside. So, whenever there is a difference in potential, there has to be a flow. And from Ohm's law, we also know that when we have a potential difference and flow, there has to be a resistance. Generally, flow is proportional to the potential difference, and the proportionality constant is the inverse of resistance. Okay. So, there has to be that is the starting point of defining something called surface resistance to radiation. It's essentially, it accounts for the flow between EB and J, and the potential difference and the heat flow, they are connected by the factor surface resistance to radiation. So, that is the first concept which we are going to look into this class. So, what we see here is the picture of one zone which has the area, emissivity, temperature, and reflectivity. This is the radiosity, and I have some amount of irradiation on the surface. As a result of this interaction between G, E and J, some net amount of heat leaves the surface or it is to be added to the surface. So, Gi is the irradiation on the surface, Ji is the radiosity, and Qi is the net radiation flux. So, of course, Qi would be equal to Ji minus Gi. where Qi is defined as the amount of energy that you have to supply to the surface to maintain its temperature at Ti. So, this Ti we are keeping fixed by adding some amount of energy to it. Ji is a radiation flux leaving the surface, as can be observed by someone standing immediately just immediate outside of the surface. Gi is the irradiation which is assumed to be uniform over the whole surface Ai. So, if you think make the balance, Qi is simply going to be Ji minus Gi. Now, I can express Ji as epsilon I Ebi plus rho I Gi. This is the emission from the surface, this is the reflection from the whatever is irradiated on the surface. So, Ji is simply the sum of these two. And since I have it's an opaque object, so alpha plus rho would be equal to 1, transmittivity is equal to 0, and since it's gray, alpha is going to be equal to epsilon. So, epsilon plus rho would be equal to 1, epsilon I plus rho I would be equal to 1. Now, what we are going to do is we are simply going to substitute these and trying to find out a relation between J and E. That is our objective. How do I find out a relation between Ji and Ebi? So, first I have to substitute rho I and I have to substitute Gi in terms of something that we know of. So, it's simply Ji would be equal to epsilon I Ebi plus 1 minus epsilon I times Gi. This comes from whatever we have written over here. Are all of you with me? Okay, I'm not doing anything new, I'm simply rearranging the things. Since Qi is equal to Ji minus Gi, which we have said before, so I can substitute the things, substitute Ji and Gi in the form that Qi would be equal to epsilon I Ebi minus Gi. That is straightforward. This comes from the relation, the last relation which I have written in the previous slide, Ji minus Gi.
So this Qi shouldn't be Gi minus Ji.
Okay. Yes, that's a question which I was expecting. Shouldn't Qi be equal to Ji minus? I mean the opposite of this, Gi minus Ji. If I also thought that if I make a balance across this, then Qi and Qi plus Ji should be equal to Gi, which would give rise to Qi as Gi minus Ji. Now, it would be I probably have drawn it in a different way, but my definition was Qi is the energy that you have to supply to the surface. You have to supply to the surface to maintain its temperature at a constant value. So, Qi is more like this one that we have. Okay. So, we are trying to simplify the equation as this and then I have Gi so these are certain steps which I am simply there is no new concept involved. Let us see what we have done. Starting with the definition of Qi, realizing the fact that alpha plus rho is equal to 1 and it is a gray object. So, alpha would be equal to epsilon. I have this relation, as well I have the relation for Gi. So, I start with Qi, substitute Gi which is unknown to me because I do not know how much irradiation I am going to get in an enclosure. So, I express everything in terms of Ji and after simplification I get this. So, this is potential of the surface, this is potential just outside the surface. The difference in potential is equal to the heat flow. Are we clear about it? potential of the surface itself, which is inherent at its because of its temperature Ti, the potential just outside the surface. If these two are not equal, then the difference in potential would definitely result into some sort of heat flow in between the two, and that flow is denoted by Qi, and what we see is they are related by this one, epsilon I by 1 minus epsilon I. So, if I talk in terms of the total amount of heat, it is Ai Qi, which would be Ai times epsilon I by 1 minus epsilon I and Ebi minus Ji. So, if you think of some in terms of Ohm's law, then the resistance is 1 minus epsilon I by Ai epsilon I. This is known as the surface resistance to radiation. Okay. When you have a real surface, for which case Ji and Ebi are not equal, then the inequality for an opaque surface which is irradiated uniformly, that resistance is simply 1 minus epsilon I by Ai epsilon I. And if you think of a black body, what is going to be the value of this resistance? If it is a black body, resistance, its resistance is going to be 0. Okay. So, if the resistance in between two potentials is 0, what can you say about the two potentials? They are same potentials. So, for a black body, E and J are same, which is consistent with our understanding. But for any other surface, there would be some amount of transfer from an object to the outside, and the amount of transfer is known to you if you know what is E and what is J. All right. So, that's known as the surface resistance to radiation, and now we are going to use this concept for radiation between two surfaces when it is forming a two zone enclosure. Any question up to this point? Okay. So, you can also find out what is going to be the unit of Ri. Is it what is going to be the unit of Ri? Simply 1 by meter square. Okay, fine. Let us see our first and simplest possible enclosure, which is two zone. What is a two zone enclosure? Okay. Now, what is an example of a two zone enclosure where radiation is taking place? When can you say that two zone is sufficient to form an enclosure? Can you give an example? Yes, what is this cylinder? Two concentric cylinders. That's a very valid example. Two cylinders concentric with each other, and the outer surface of the inner and the inner surface of the outer are exchanging radiative heat. Okay. You are going to see many such applications in engineering, okay, which is forming two zone enclosure. If you have two very large parallel plates, and if I put them close to each other, then the area of these two surfaces, if that's too large compared to the gap in between the two, then that's also a two zone enclosure. Okay. You have two surfaces lying very close to each other. So, these are examples of two zone enclosure. So, let us start with an hypothetical figure of zone 1 and zone 2. Both these surfaces are opaque, and you have same amount of irradiation on all the surfaces, which you can see is not going to be true if the surface 2 looks like this. So, this zone is obviously going to get less amount of irradiation. Now, let us say that this area is Ai, its temperature is T1, A1, T1 and epsilon 1, whereas this one is A2, T2 and epsilon 2. So, I am going to think about these. I have to add some amount of heat here and some amount of heat here. Let us call these as Q1 and Q2. Okay. and let us assume that we are going to reach steady state. All the analysis that we are doing is at steady state. I would like to find out what is Q1 to 2. That means the net radiative heat transfer between zone 1 and 2. Okay. Q1 to 2, what amount of energy is going from 1 to 2? Would you be able to tell me? And these J1 and J2 are known to we define some radiosity as J1 and J2. Okay. So, what is the total amount of energy that is leaving A1 or surface 1? J is watt per meter square. So, I multiply J1 with A1. All right. So, of this, the amount that is leaving, which is equal to A1 J1, that means in watts, what fraction, some fraction of it is going to strike 2. Okay. So, it has to be F12. So, this is the total amount of energy which is emitting from surface 1. The fraction which is striking 2 is F12. So, A1 J1 F12 is the amount of energy emitted by 1 which is going to strike 2. And this one, the surface 1 is also going to get some amount of energy from 2. What is that amount of energy? Which would be a minus sign, A2 J2 F21. So, that is the net amount of heat which surface 1 is giving to surface 2. That part is clear. All right. Now, any simplification that comes to your mind in this? Fine. Reciprocity relation, these two would be equal, A1 F12, A2 F21. So, I can say that Q1 to 2 is simply going to be A1 F12 times J1 minus J2. Okay. And of course, this can also be written as J1 minus J2 by 1 by A1 F12. So, now you see that you have two more potentials, one just outside surface 1, the second just outside surface 2. Okay. And these two are connected by a resistance which is equal to 1 by A1 F12. So, if this is my EB1, which is known, whose absolute value is known to me if T1 is known to me, and if this is EB2, whose value is known to me since I know temperature, then there are two more potentials. One is J1 just outside the surface of 1, and the second is J2 which is just outside of surface 2. These two are connected by a resistance whose magnitude is equal to A1 F12. And these EB1 and J1, these are connected by two more resistances which we have just seen as 1 minus epsilon 2 by A2 epsilon 2, and this is 1 minus epsilon 1 by A1 epsilon 1. Okay. So, that is basically your the whole picture. Now, is this part clear to all of you? Okay. So, if I would like to find out what is the total amount of energy transfer, net amount of energy transfer between 1 and 2, then I simply have to find out what is the potential difference divided by the sum of all resistances. All resistances means resistance 1, 2 and 3. One is surface resistance, the second due to the view factor and all, and the third is another surface. Between two surfaces, radiation exchange between two surfaces is always going to be 3 resistances unless one of the surface is black. Okay. So, if one surface is black, then one surface resistance disappears. All right. Then you have 2 resistances. If both the surfaces are black, then these 2 surface resistances will disappear, but you will still have the view factor part, which you have seen before, all right, which is Stefan-Boltzmann law in a different way. So, and you can also say that Q1 has to be equal to minus Q2 in order to maintain thermal equilibrium. So, whatever energy that you are putting in 1 has to be taken out from 2 or vice versa in order to maintain thermal equilibrium. for 2 zone enclosures, which would not be true for a 3 zone enclosure, because the amount of energy that you are giving to surface 1 can very well get distributed between 2 and 3. So, Q 1 equals minus Q 2 would be valid only for 2 zone enclosures. Okay. Since we have understood 2 zone enclosures, it would be very easy to form a 3 zone enclosure, which is the most common this is the most common that you would see, okay, and we are going to solve certain problems on this. A 3 zone enclosure, a surface of a furnace, it's enclosed, one surface is the where you would like to hit the object. So, you put the object that you would like to dry on this surface. This is the surface where you are adding some amount of electrical energy, and you form another surface which does not take part into it, but which forms the enclosure. That's what you can think of as the simplest enclosure problem. So, you are adding some amount of energy, this amount of energy is received over here, and these ones are at a certain temperature. But the amount of energy that you add here, you cannot say that this is equal to what is being received by this. Okay? It is going to taken up by this one, and this surface is not only going to receive energy from this hot surface only, it is also going to get some amount of reflected energy from surface 2. Okay. So, these 3 surfaces interact with each other in all possible ways, but we would like to simplify this utilizing our concepts of surface resistance and whatever be the resistance for heat transfer in between 2 surfaces when the radiosities are known. So, how many potentials can we think of for a 3 zone surface? One is the inherent potential, which is EB1, EB2 and EB3. So, let us mark as EB1, EB1, EB2 and EB3. These would be known to you provided you know the temperature of the surface. Now, what are the other potentials? Each surface has a potential which is the radiosity. So, I put a radiosity for each of the surfaces which is J1, J2 and J3. This is volumetric phenomenon. Okay, the amount of energy that this surface is going to emit had this been a black body. This is what it is actually emitting. So, it depends on the value of emissivity, and it also depends on whatever be the irradiation surface 1 is receiving from other and what part of the incident radiation it is reflecting. So, that is why J1 and EB1 are connected by a resistance. What is that resistance going to be? 1 minus epsilon 1 by A1 epsilon 1. I am going to have another resistance in between J2 and J3 and EB3, which is going to be 1 minus epsilon 3 by A3 epsilon 3, and this resistance is going to be right. So, that is the 3 all the potentials I have marked over here. If this is a 2 zone enclosure, that means only J1 and J2 are there, what would be the resistance in between the 2? Okay. So, 1 is going to interact with 2 as if it is a 2 zone enclosure. So, its resistance is going to be 1 by A1 F12. 2 is going to interact with 3 through a resistance A2 F23, and 1 is going to interact with 3 as if it is A1 F13. So, that completes our circuit for a 3 zone enclosure. So, one part is the surface resistance and second is the interaction between the 2 surfaces. Now, you understand that this is interaction between 1 and 3. We also know that 1 can interact with 2, 2 can interact with 3. So, you have something which is pretty much well known to you from another subject, which is okay. You can have star delta combination, you can have delta, you can convert from one to other, you know the methodology. And the same way you have done for electrical technology, there are certain things which you can specify. What can you say about any of these nodes, inner nodes? How do you solve, find out the current or anything at the inner node? Summation of currents at any node would be equal to 0. Summation of energy at any of these nodes would be equal to 0. Absolutely no difference. And that is what you expect, because at steady state, whatever amount of energy is coming to this, this and this, algebraic sum of the three would be equal to 0. So, if you know certain things, let us say the EB1, EB3 are known to you, you also know the view factors, you also know what is epsilon 1, epsilon 2, epsilon 3, you are asked to find out what is the temperature of surface 2. Okay. So, what you do is, utilizing all those, you try to find out what is the value of J2. Since epsilon 2 is known to you, you can calculate what is the value of EB2. The moment you know the numerical value of EB2, it is going to be equal to sigma T to the power 4. T2 is the only unknown. And all the techniques, tricks that you have used for electrical technology would be equally applicable here. But the basic thing, most basic thing that we have to know is the sum of currents at any node would be equal to 0. Sum of energy at any of these nodes would be equal to 0. All right. There is another consideration which we can make is radiating surface. There are some zones where you can see that it is perfectly insulated. It is not a black body, but this is perfectly insulated. So, if it is perfectly insulated, let us examine what kind of advantages or what kind of modifications to this approach we will have to make. If something is perfectly insulated, how much energy you are adding or extracting from outside? 0. So, if you are not adding anything from outside or extracting anything from outside, what is the current between this? Let us say this is surface 2, current would be 0. So, if the current is 0, what can you say about EB2 and J2? They are equal. So, for a radiating surface, radiosity and your emissive potential, they are same. You understand the reason why it is so. So, for a radiating surface, EB is equal to J, EBI is equal to JI. Since you do not extract anything nor you add anything. So, there is no current in between these two, and these two potentials will have to be the same. So, the figure for this is going to be simply one resistance, surface resistance between surface or two surfaces, the other one this and this, no current through this. So, this and this are in series, this is parallel to the sum of these two, and then everything is in series. That is pretty much straightforward, you all know about it. So, a radiating surface is very common in many of the engineering applications where you would like to have the outside walls of the furnace almost very close to insulated as you can. So, in certain cases you can assume that one surface is perfectly insulated, you do not add or extract any heat to the surface. If that is the case, that there will not be any difference between radiosity and the inherent emissive potential. But that does not mean that it is a black body. It will still not be a black body, but for the special condition that you are attaching to it, it behaves as if J1 and J2 and EB2 are the same. That is called a radiating surface. All right. Then in the remaining time that we have, I am going to talk about a problem, discuss about the steps and give you the answer. So, what we have is an oven which is in the shape of an equilateral triangle. Okay. This surface is perfectly insulated and you have an epsilon 1, the value of which is given, T1 is at 1200 Kelvin. This is the radiating surface with epsilon r is 0.8 and the temperature of this is, let us denote it by Tr. The width of the any of these is equal to 1 meter. This epsilon 2 is 0.4 and T2 is 500 Kelvin. What you have to, this is a baking oven which consists of a long triangular duct in which a heated surface is maintained at 1200 degree Kelvin and another surface is insulated, which is the R surface. Painted panels which are maintained at 500 Kelvin occupy the third surface. The triangle is of width 1 meter on a side and the heated and insulated surfaces have an emissivity of 0.8. So, both these surfaces have emissivity 0.8. The emissivity of the panels is 0.4. During steady state operation, at what rate energy must be supplied to the heated side, that means what is the energy that you supply to this side per unit length of the duct to maintain its temperature at 1200 Kelvin, and what is the temperature of the insulated surface. So, in order to maintain this surface at 1200 Kelvin, you have to supply energy from outside, which is obvious, and what is this surface is perfectly insulated. So, its temperature will also be something which you have to find out, and of course, the painted panels are kept here at 500 Kelvin. So, that means you are extracting heat from these sides. At steady state, whatever you are adding here has to be equal to whatever you are extracting from here, and since this being insulated, its temperature you have to find out, and what is the heat that you are adding to surface 1 to maintain its temperature at 1200 degree. That's you have to find out. Now, whenever you come across such a problem, the first thing that you should do is draw the circuit diagram. Okay. You draw the circuit diagram, then identify and compute, calculate each of those resistances, and then it would be a simple case of solving the problem. So, let us see, I am going to have some EB1 and the magnitude of EB1 sigma 1200 to the power 4, okay, that many watt per meter square. Then that is going to be some resistance and a J1. I have surface 2 which is EB2, the value of which is sigma times 500 to the power 4, and this is in connection with J2 and then I have some resistance between J1 and J2. What is the resistance between J1 and J2? 1 by A1 F12. I have something called JR. All right, JR is for this surface. You can stop me anytime if you want some more clarification. So, this JR and J1 and JR and J2 are also connected. This is going to be 1 by A2 J2R and this is 1 by A1 F. I am sorry, F, this is F, F1R, all right, and then I am going to have EB3, and this resistance EB3 is sigma TR, which is unknown, to the power 4, all right. Since this is an insulated surface, it is a radiating surface, so these two are equal. This resistance does not exist. So, in order to find out the temperature of surface R, the quantity that you would like to evaluate is what is JR. If you can find out JR, your problem is solved. And you are adding some amount of heat here, you are extracting the same amount of heat out here. All right. That in order to maintain steady state, whatever amount of heat that you add here is the amount of heat that you take out from here. Now, what is the amount of heat that you add here? The amount of heat that you add here is simply the potential difference between these 2 points divided by the sum of all, I mean the equivalent resistance, and this one are in series, this and this in parallel with this one. So, you can find out what is the equivalent resistance of these these three resistances, and then that equivalent resistance is going to be in series with this and with this. That is it. So, the magnitude of this is known, magnitude of this is known. What is the value of F12? An equilateral triangle, 0.5. Equilateral triangle means any energy coming out of one surface has equal probability to go to the two other remaining surfaces, since it is equilateral triangle. So, F12 is all the view factors, individual view factors, F11 would be 0, F12 would be 0.5, F13 would be equal to 0.5, same for all surfaces. So, you know what is this F1R, F12 and F2R, numerical values known to you. Areas are either known to you, or you can take the area outside and express it in terms of flux, the energy that is going in terms of flux. So, I suppose you should be able to find out what is Q1 to 2, which is EB1 minus EB2 sum of all resistances. So, that way you can find out what is the total amount of energy that flows from here to here. Now, how do you find out JR? Let me ask you, is there any question how you evaluate Q1 to 2? I think all of you understood. Any question? So, the next part is I have to find out what is TR, magnitude of TR. In order to find magnitude of TR, I have to know JR. How do I find out JR? Flow from J1 to, this is J1, J1 to J2 is known, EB1 to EB2 is known.
EB1 to J1 is known. So
Would you be able to find out what is the numerical value of J1? Is there any way of, your EB1 is known, the resistance is known, the flow is known. So, J1 can be found out. All of you are with me. EB2 is known, resistance is known, flow is known. So, J2 can be found out. So, suppose I know the numerical value of J1 and J2. After that, the current that comes from J1 to JR has to be equal to the current that comes from JR to J2. The flow in this direction, since it is a radiating surface, has to be equal to this one, or rather the algebraic sum of heat at node R should be equal to 0. So, your J1 is known to you, J2 is known to you, all the resistances are known, only unknown JR. JR can be found out. Once you have JR known to you, JR is simply equal to epsilon T to the power R. Right. So, you not only you find out what is the, for steady state operation of this furnace, how much energy you are supplying from outside, you also find out if there is an insulated surface which has to be there has to be there for a furnace, what would be the temperature of the furnace, what would be the temperature of that wall. Any question about the methodology? Okay. The answers that you have the amount of energy that you have to add per unit length is 37 kilowatt per meter. That is the amount of energy you are adding to surface 1. And the temperature of the insulated surface is equal to 1102 Kelvin, okay, which is expected. It is insulated, so its temperature must lie between this one and this one. So, that is what you have. So, now what we have done in this class then is we have understood the limitations, the assumptions involved in network exchange. Which are the assumptions that are may not be valid all the time? Perfect irradiation, same irradiation, and same amount of emission from the surface irrespective of the area. we have found out what's the surface resistance to radiation, the relation between EB1 and J1. We have also seen when two surfaces interact, what is the resistance in between the two, which is simply 1 by A1 F12. So, when two such surfaces form an enclosure, there are three resistances, two surface resistances and one resistance between J1 and J2. We introduce three zone enclosure, that is the most common one. So, I am going to get 1, 2, 3, three surface resistances and three resistances in between. So, total 6 resistance. And there can be something called a re-radiating surface, which is not a black body, but for which case J3 is equal to EB3. But again, I am emphasizing re-radiating surface is not a black object, but it behaves as if J3 is equal to EB3. And then you have the usual circuit type of things that you have been exposed to before, and you can solve either for the amount of heat to be added to a surface or the unknown temperature of any of these surfaces. Okay. So, we will continue with that in our next class. Thank you.